Hello everyone. Today I'm going to be working on Webwork Homework 16, problem number 9. Now the reason that I liked this one is that actually once you get it set up, it's relatively easy. But it's a new concept that actually we didn't get explicitly taught, but there's no reason we shouldn't be able to do it based on what we already know. It works on a partially decoupled system. See, we actually have two different differential equations. We have dx dt equals y minus x plus t, and we have dy dt equals y. If we can solve one of these, and I already gave away which one we're going to use, it's going to be the dy dt because it's easier. If we can solve this, then we can plug in the y that we get for this in terms of t straight into here, and then we can solve this. So it's easier than it looks. So let's just focus on solving this. This is super easy. I did it with the characteristic equation, but you could have done this the way that we did in the first unit, where you take 1 over y dy and move over the dt, but I've been doing this a lot, so I just like this. I had y prime minus y equals 1. I created the characteristic equation, m equals 1, so it's y equals c1 e to the t. I plugged in my initial condition. The y of 0 is 6, so 6 equals c1 e to the 0. So c1 is going to be equal to 6, so y is 6 e to the t. Now we can take that 6 e to the t and plug it straight into our original differential equation. So dx dt, 6 e to the t minus x plus t. We can create a characteristic equation again. X prime plus x is 6 e to the t plus t. Just moved over the x. For the characteristic equation, I've got m plus 1 is 0, m is negative 1, so that means our characteristic equation is c2 e to the negative t. Then the particular solution, I had a e to the t, bt, and c. And then you only need to do one derivative because you only have one derivative in the original equation. So a e to the t plus b, plug it all in, and you get this is going to be equal to 6 e to the t plus t. And I broke it up into 3 different parts because each of these is going to be linearly independent. So I know 2a e to the t is going to be equal to 6 e to the t. 2a is 6, a must be 3. bt equals t, b must equal 1. B plus c is 0. We know from here that b is 1, so c plus 1 is 0. C must be negative 1. And then, so your characteristic polynomial, a e to the t plus bt plus c, 3e to the t plus t minus 1. So x equals your arbitrary constant, e to the t plus 3e to the t plus t minus 1. Plug in your initial value, that x of 0 is 3. And you get c2 plus 3 minus 1 is 3. c2 ends up being 1. And x equals e to the negative t plus 3e to the t plus t minus 1. So essentially, it's super easy. All you need to do is you're just taking this original these two equations, solving one of them, and then plugging it in right into there. And the actual things themselves are super easy because it's only first order. So that is just about it. I hope that you found this useful. It's really just a slightly new concept. It's nothing that's really legitimately new. Thanks. That's it. Bye.